Welcome to this video on the Transmission Control Protocol or TCP. In this video, we will explore the fundamental concepts of TCP, its importance in networking, and how it enables reliable communication over the internet. TCP is important because it ensures reliable and accurate data transmission over the internet. Here are the main reasons. TCP makes sure that the data sent by the sender reaches the receiver without errors. If any packets are lost, TCP retransmits them. It ensures the data packets arrive in correct order, which is crucial for applications like web browsing and file transfer. TCP can detect errors in data and request retransmission if necessary, ensuring that the integrity of the data. It adjusts the rate of data transmission so the receiver is not overwhelmed with too much data at once. TCP reduces the speed of the data transmission if the network is congested, helping to prevent data loss and delays. TCP establishes a connection between the sender and the receiver before data transmission, which makes communication more reliable. TCP uses three-way handshake. Handshake refers to the process to establish connection between the client and the server. Handshake is simply defined as the process to establish communication link. The three-way handshake is the method used to establish a TCP connection between a client and server. This process ensures that both parties are ready to communicate and can reliably exchange data. Here is a detailed breakdown of each step. The first step is synchronize. The initiator is client. The client sends a synchronous packet to the server indicating that it wants to establish a connection. The packet contains the initial sequence number that the client will use for the communication. The second step, synchronize acknowledge. The initiator is server. The server receives the synchronization packet and responds with a synchronization acknowledgement packet. The synchronization acknowledgement packet acknowledges the client's synchronization request and includes the server's own initial sequence number. This packet indicates that the server is ready to establish a connection. And the third one is acknowledgement. The initiator is client. The client receives the synchronization acknowledgement packet and sends an acknowledgement packet back to the server. This acknowledgement packet acknowledges the receipt of the server's acknowledgement. Once this packet is sent, the connection is fully established and the data can be exchanged between the client and the server. The TCP header is a crucial part of the transmission control protocol, providing essential information for managing the connection and ensuring reliable data transmission. The TCP header is typically 20 bytes long, but it can be longer if options are included. Here is a breakdown of the TCP header files. Source port 2 bytes, the port number of the application that is sending the data. Destination port 2 bytes, the port number of the application that is receiving the data. Sequence number 4 bytes, this number indicates the order of the data being sent. It is used to ensure that data segments are reassembled in the correct order at the receiver. Acknowledgement number 4 bytes. This number indicates the next expected sequence number from the sender. It is used to acknowledge the receipt of the data. Data offset, also known as the header length. This field indicates the length of the TCP header in 32-bit words. It helps determine where the data begins. Reserved bits, 3 bits. This field is reserved for future use and should be set to 0. Flags, 9 bits. These control flags indicates the state of the connection and specific action. Window size, 2 bytes. This field specifies the size of the sender's receive window or buffer size and indicates how much data can be sent before receiving an acknowledgement. Checksum 2 bytes, a checksum for error checking the header and data. It helps detect any corruption that may occur during transmission. Urgent pointer, variable length. This field indicates the end of the urgent data if the urgent flag is set. It provides a pointer to the location of urgent data within the segment. Options. This field is optional and can be used for various purposes such as specifying maximum segment size or enabling selective acknowledgement. Padding variable length used to ensure that the TCP header is aligned to that to 32-bit boundary. Error control in TCP ensures reliable data transmission by detecting and correcting errors. Here are the main mechanisms involved. Checksum. Each TCP segment has a checksum that checks for data corruption. If the receiver's calculated checksum does not match the one in the header, the data is considered corrupted. Acknowledgement. The receiver sends acknowledgement back to the sender for successfully received segment. If the sender does not get an acknowledgement within a certain time, it retransmits the segment. Retransmission. If a segment is missing or corrupted, TCP will resend it to ensure that the data reaches the receiver correctly. Sequence numbers. Each byte of data is assigned a sequence number helping the receiver put segments in the correct order and track missing data. Selective acknowledgement. This optional feature allows the receiver to tell the sender which segments have been received, so only the missing segments are retransmitted, improving efficiency. And finally, timeouts. TCP uses timers to determine how long to wait for an acknowledgement. If none is received within the timeout period, the segment is resent. Flow control in TCP ensures that the sender does not overwhelm a receiver with too much data at once. Here is a simplified overview. The first one is window size. TCP uses window size to indicate how much data the sender can send before needing an acknowledgement from the receiver. The receiver tells the sender how much buffer space is available. Sliding window protocol. The sender can send multiple segments of data up to the window size without waiting for acknowledgement for each one. As the sender receives acknowledgement, it can send more data. Dynamic adjustments. The window size can change based on how quickly the receiver processes the data. If the receiver's buffer is full, it will reduce the window size signaling the sender to slow down. Buffer management: the receiver manages its buffer to prevent overflow. If the buffer is nearly full, it tells the sender to send less data to avoid data loss. Congestion control interaction: flow control works alongside congestion control, which helps manage overall network traffic. Congestion control in TCP is a mechanism that manages network traffic to prevent congestion, ensuring efficient data transmission across the network. When too many packets are sent by the network, it can lead to packet loss, delays, and overall degradation of service. Here is how TCP implements congestion control. Congestion window is a variable that controls how much data can be sent before needing an acknowledgement. It helps the sender manage its data transmission rate based on current network condition. Slow start: TCP starts in slow start mode where the congestion window begins at a small size, usually one segment. The window size doubles with each acknowledgement received, allowing the sender to increase its sending rate rapidly until it detects congestion. Congestion avoidance: once the congestion window reaches the threshold, TCP enters congestion avoidance mode. In this mode, the window size increases more slowly, typically by one segment for every round trip time to prevent congestion. Fast retransmit: if the sender detects that a segment is lost, it immediately retransmits the missing segment without waiting for a timeout. This helps quickly recover from packet loss. After the fast retransmit, TCP enters fast recovery mode, where it temporarily reduces the congestion window but avoids going back to slow start. This allows for a smoother recovery and faster data transmission after a packet loss. If an acknowledgement is not received within a certain time frame, TCP assumes congestion has occurred and reduces the congestion window size. This helps the sender back off and reduce the traffic on the network. Here are the pros of using TCP. Reliable data transmission: ensure that the data is delivered accurately and in the correct order through mechanisms like acknowledgement, checksum, and retransmission. It manages data transmission to prevent overwhelming the receiver, ensuring that data is processed efficiently. TCP adjusts the sending rate based on the network condition to avoid congestion, which helps maintain network performance. TCP establishes a connection before data transfer, ensuring a reliable communication channel between sender and receiver. TCP includes error checking mechanism to detect corrupted segments, allowing for data integrity during transmission. TCP treats data as a continuous stream of bytes, allowing applications to send and receive data without worrying about packet boundaries. Here are the cons of using transmission control protocol. Overhead: the reliability features of TCP introduce additional overhead in terms of data and processing, which can lead to reduced throughput in high-speed networks. The connection establishment process, for example three-way handshake, and the need of acknowledgement can increase latency compared to the connectionless protocols like UDP. The delay from retransmission and acknowledgement makes TCP less suitable for real-time applications like gaming or video streaming where speed is crucial. TCP requires more memory and CPU resources and both the sender and receiver to manage connections, maintain state, and handle retransmission. The TCP header size is typically 20 bytes, which can be considered relatively large for small packets, leading to inefficient use of bandwidth for small data transfers. Thank you for watching.